Alrighty, so we are now going to start working on the next set of physics problems, which is, as I said before, a completely different system of solving physics. So we had kinematics, we had Newton's laws, and then we had energy. And each system was good at the particular problems it was good at. Energy allowed us to solve really complicated sounding problems, but to do it in a fairly easy way by taking advantage of the conservation of energy. Newton's laws, that was good for dealing with forces, how heavy something is, pushing and pulling on objects, things like this. And of course, kinematics was good for basic motion, the dynamics of a system, things moving along, accelerating, and you want to know how long it'll take to get somewhere and things like this. Each one has pros and cons about it, and each one has its own set of equations, and you kind of stick in its realm for its types of problems. Well, now we're coming on the next set, but the good news is it is, you will find, basically a complete repeat of kinematics. So all of the stuff we learned about kinematics, velocity, acceleration, distance traveled, things like this, they're going to be back again, but they're going to be back in kind of a special way. All of those old kinematics problems dealt with objects which moved in a straight line. It may have accelerated, it may not have accelerated, but things were always moving in the same direction. So a car is moving to the east, maybe it slows down, maybe it speeds up, whatever. But it wasn't turning, it wasn't moving in different directions. Well, now what we're going to deal with is sets of systems where objects are allowed to move in circular motion, basically. So, at first it's going to seem kind of weird. We're going to have a whole new set of variables, but I promise you, if you wait till the payoff, you will see that if you can do your old kinematics problems, these are going to be identical. So let's get started with it. The first thing I want to do is list the old kinematics, and I'll call it linear kinematics. So that is the kinematics of a system that moves in straight lines, all in the same direction. What were the variables that we had to deal with? Well, we had x, which was like distance, how far something went, or displacement. We had v, was velocity. We had a, acceleration. What if the velocity changes? Of course, we had t for time. And of course, we can continue on with the variables. What other linear variables did we know? We know momentum, p. Kinetic energy, 1/2 mv squared. F for force. M for mass. All of these variables we had in physics thus far, and we're fine with them. We've used them in equations and so forth, so we're kind of used to them. Well, now what we're going to do is go to rotation land. So in this version of physics, instead of a car moving in a straight line, a car driving 60 meters per second north for 10 seconds, these are going to be things like a wheel is spinning, and it spins around so many radians per second. Or the tires of a bicycle as a bicycle speeds up or slows down, or a propeller on an airplane, or a car going around a racetrack. All of these systems are going to be systems where an object or a system moves in circular motion. Now, I'm going to call that rotational, or sometimes I'll also use the word angular. And just know that they mean the same thing. If I talk about rotational kinematics, it's the same as saying angular kinematics. It just means in a circle. So I've had different teachers in my physics career, obviously. And some teachers use rotational, some teachers use angular. And so I have it all mixed up in my mind. You know, they both mean the same thing to me. So sometimes I'll say angular velocity. Sometimes I'll say rotational acceleration. Both mean angular or both mean rotational. Don't be confused if I use angular. Anyway, it turns out that this version of physics that deals with rotational motion has exactly the same types of variables as the linear version, but its own. Only they're the rotational version. So, just as in linear physics, x means distance, how far something goes, in rotational kinematics, we have theta, which means angular displacement. And angular displacement basically means this. Let's say you have a tire that's spinning, and you put a mark on the tire so you can watch the mark and see how far around it goes. Theta, or angular displacement, means how far around, how many times around, or how many degrees in a circle the tire spun. So, for instance, if the tire makes one complete revolution, the angular displacement is 2 pi radians. And that's important. The units are radians, not degrees. Degrees is fine for angles, you know, your cannonball is shot at an angle. But in kinematics and rotational kinematics, the distance we're going to talk about for an angle is going to be radians. And so, you know, maybe the wheel spun 3.5 rotations, 3.5 revolutions. Well, that's going to be 3.5 times 2 pi radians, because each 2 pi is one of the revolutions. Okay, so angular displacement is also like a distance, but instead of it being a linear distance, how far something went, it's how far around something spun. But in your mind, you relate theta, angular displacement, with x for distance. They're both kind of the same thing. Velocity v in linear, the rotational version, is called omega. That's a Greek letter. It's like a curly W. And that's angular velocity. Radians per second. So again, ball is thrown at 5 meters per second. Here, a tire is spinning at 4 radians per second. It's like how many times per second the wheel spins, like a velocity. Acceleration A becomes alpha. I've got another Greek letter. The Greek letter for A is alpha, and that's angular or rotational acceleration. So again, a car can speed up, it can accelerate. Well, a wheel that's spinning can speed up its spin or slow down its spin, so it can accelerate as well. That would be an angular acceleration. Time doesn't change. Time is t, no matter if you're talking about linear kinematics or rotational kinematics. Time is time. That's not different. Now these other ones, they are a little different. P for momentum becomes L, angular momentum. There's the linear kinetic energy. There's also the rotational kinetic energy, which I'll show you in a little bit. F for force, so you push on an object. Well, there's a rotational version of a force, which is a force which makes something rotate. So you think about like a bolt. Here's a bolt. There's a wrench. And you want to tighten the bolt. You push on the wrench, which rotates the wrench down, rotating the bolt. Well, that type of force which causes this rotation is called, tau, the Greek letter tau. It's called torque. Now, you've probably heard the word torque before. Usually, cars, they talk about how much torque the engine gives to the wheels, or how much torque can you apply on the bolt with this wrench. A longer wrench gives you more torque. The rotational version of a force is called a torque, and it's tau as the letter. Mass, there's a version of mass that has to deal with rotation, because if you think about it, let's say you have a metal bar. Okay, if you grab it from the center, imagine doing this, really long, heavy metal bar. You grab it from the center and you try to rotate it around. Okay, it's heavy and it takes a certain amount of force, a certain amount of torque to try to rotate it. But then imagine grabbing it from the end over here, and so you get this big, long pole extending away. And then you try to rotate that. I think intuitively, and you've probably done this before, it's harder to rotate it from the end with all of the poles sticking out than it is to rotate it from the center. And the reason is because when you're at the end, most of the mass is away from your hand. So the mass of the bar is located further away from where you're applying the force. Whereas if you put your hand in the center, then you're kind of in the middle of the bar, so all of the mass is near where you are, and so it doesn't take as much force to rotate it. So there's a concept of a mass that has to do with how easy it is to rotate something, and it's called I, moment of inertia. It's basically like a mass, but it takes into account where is the mass located relative to a point of rotation. Okay. And now that I have this, I can go back to kinetic energy and tell you what the equation for kinetic energy is. Instead of m, we have the rotational version of mass called I, and instead of v squared, we have omega squared. So the reason we have to worry about a rotational kinetic energy is, think about this. Let's say you have a record player, and the record is spinning on the tabletop. Okay. Well, if you were asked, is there any kinetic energy built into that record? You say, well, kinetic energy is 1/2 mv squared. V is the velocity. The record's not moving; it's just sitting there rotating. So the velocity is 0. So I'd have to say there's no energy associated with its motion. So no kinetic energy. But obviously, there is some energy, because it doesn't just rotate by itself. You have to do something to make it rotate. And it is moving. It's just not moving to the side or up and down. It's staying in place, but it is moving by rotating. And so, in order to account for the motion of rotation for energy, we need a rotational version of kinetic energy. And that's exactly what this is. So, this is the good news. The good news is, all of the stuff we had before for linear physics, all the physics we've been doing, there's now a whole new set of variables. They have new names, new variable names. So instead of x, we have theta. Instead of v, we have omega. Fine. But we still have in our mind how to think about the linear variables. And as long as you remember how to think about linear variables, when you have to do rotational ones, you're going to think the same way. And I'll show you what I mean by that in a second. First thing to note, now that we know what the variables are, we could go back to any equation we had in physics. So let's look at kinematics. We had x equals v naught t plus 1/2 at squared. I think we all remember good old kinematics equations. And this is one of them. Well, now that we're talking about rotational motion, we're going to need a whole new equation which deals with this type of system. How do we convert? Well, there's a certain way of converting. I can tell you what that is. If there's any time you want to convert between an angular variable and a linear variable, it goes like this. Theta, the angular version, is equal to the linear version times r, where r is the radius of the circular motion. So, for instance, if you have a bicycle wheel, we put a little dot on the wheel so we could track its motion as it's rotating. If I want to know for not v, I'm mixing my variables. Obviously, there should be x, because it's distance. Theta is a distance, so it has to be x is the distance. Sorry. If I'm talking about, for instance, this wheel is spinning, and I say, well, let's say the wheel spins so that this mark gets to here. So obviously the wheel went some amount of distance, and I say, oh, the theta was, let's say, 4 radians. And I say, okay, if the wheel went around 4 radians, then how far did the bike move? Well, that means find me x. What's the linear distance? If the wheel rotated by 4 radians, how far linearly did that make the bicycle move? Well, you got to use this equation. Theta over r. So 4 radians divided by what's r? R would be the radius of this wheel. Of course, a bigger wheel would make the thing go a lot further than a smaller wheel. A little bitty wheel like this, if it rotates to here, maybe only goes this far, but this wheel goes this far. For the same 4 radians, a huge wheel goes a very large linear distance, whereas a little bitty wheel goes a very small distance. Now, just thinking about that, is there anything that you can look at with what I've done here that seems incorrect? I want you to think about this. Pause the video if you have to. I want you to think about this. I find it's very important that when you're trying to learn physics and you're going over these concepts, that you don't just accept things. You don't just, listen to things and write things down and not think about them until later. You have to be thinking while you're learning. Activate your mind. If what I said is true, that a very large wheel, given a certain distance around the wheel spins, let's say it spins 1 revolution, it's going to move a certain linear distance. If a very large wheel in 1 revolution travels a lot further than a very small wheel, then is this true? Well, the way to see it is right here. Look at what I wrote. The linear distance traveled is the angular distance, the 1 revolution, divided by the radius. When is this big? Given that this is always the same number, if r goes really small, this number gets very big. The other way to think about it is if r is very big, it's something over a very big number. That's a small number. So this is wrong. That can't be true. And if that's not true, then there's something wrong up here. So really, what you need to do is look at it and say, this guy's BSing me. The actual relationship is the linear distance is the angular distance times the radius. That way, notice here, if r is a very big number, then x gets very big. If r is very small, then x is very small. And it makes sense. A very little bitty wheel, if it goes one little revolution, it only moves a small amount. If you have a very big wheel and you go one revolution, you move a fairly large distance. So this is the real equation, the relationship between the linear version and the angular version. And this holds for all of these variables. So just as x is theta times r, v is omega times r, a is alpha times r, and so forth. Now, why am I saying this? Because for every single equation you have, all you have to do is take this x and replace it by this equation right here. This v, replace it with this equation. This a, replace it with this equation. And when you make that replacement, you'll get your new equation. Now, it looks like it's going to be tedious and a big pain in the butt to have to do all this stuff and manipulate everything. I'll give you the good news so you don't have to go through it. The good news is, at the end of the day, take the equation and just replace the linear variable with the rotational one. So, instead of x, it's theta. Instead of v naught, it's omega naught. T remains t. A becomes alpha, and t remains t. So there's our new equation. No thinking about it, no working through it, very easy. Take your linear kinematics equation, every linear variable replaced with the rotational variable, and now you have your new equation. Here's another one. Vf squared is v naught squared plus 2ax. What's the rotational version? Well, think about it. What do you think it's going to be? What do I think it's going to be? I think Vf is going to become omega f squared. V naught squared is omega naught squared plus 2 times A is going to become alpha. X is going to become theta. Again, for every linear variable, it goes to the rotational one. Just like that. Acceleration is final minus initial over time. Well, alpha is omega f minus omega naught over time. Very easy. This is nice. This is nice because when we go solve rotational kinematics problems, we don't need new equations. I don't have to memorize new equations anymore. I already know my linear kinematics because I did that a few months ago. All I have to do is write down the linear kinematics equation and replace the variables with the rotational ones. And now I have my new equations. And in fact, after you do it a few times, you don't even have to write down the linear one anymore. You just remember, as you're writing it out, to replace the variables as you go. Now, how do I use these equations? Well, here's an example. Let's say a wheel starts from rest and begins rotating. Eventually getting to 20 radians per second in 5 seconds. What is the angular acceleration? What is the angular displacement? So that's a nice system. Here you have a wheel. The wheel's just sitting there. Then it begins to move. So maybe someone's pedaling a bike, or you're cranking a motor or something. It makes this wheel begin to spin. And what you know is that after 5 seconds, you look at the wheel is now spinning with this angular velocity. And you want to know these two things. What's the angular acceleration? And what's the angular displacement? Another thing for angular displacement is to say, how far around did the wheel spin? Okay, how many radians around did it spin? How many revolutions? Whatever you want. All right, well, this is a nice, simple rotational kinematics problem. And I'm going to go through the most basic way of solving this type of problem first. And after you become more comfortable, you don't necessarily have to go through all these steps. But in general, this is how you do it. Just like with linear kinematics, first thing you do is write down what you know and what you're looking for. A wheel starts from rest. Initial angular velocity is 0. So omega naught is 0. Eventually it gets to 20 radians per second. So its final angular velocity is 20 radians per second. And it does this in 5 seconds. Time is 5. Part A, what is the angular acceleration? Alpha is something. And part B, what's the angular displacement? Theta is something. And there we go. That's what I know and what I'm looking for. All right. Next step is what equations do we have? Well, we have x equals v naught t plus 1/2 at squared, which is actually theta is omega naught t plus 1/2 alpha t squared. And we have vf squared is v naught squared plus 2ax, which actually is omega f squared is omega naught squared plus 2 alpha theta. And lastly, acceleration is final velocity minus initial velocity over time, which becomes alpha is omega f minus omega naught over t. Okay, so this, and this. Those are my 3 equations. All right, now what? Well, one thing that I have found is helpful to students when they first start angular kinematics is to think of the problem as if it's linear first. So don't worry about the rotational version. What's the linear version? Well, an object starts from rest, gets to a final speed of 20, it takes him 5 seconds, and I want to know an acceleration. So I know v naught, I know vf, and I know t, and I want a. What equation can I use to get this a? Well, this one. So I would say a is vf minus v naught over t, but I don't want the linear one, so just make it angular. Alpha is omega f minus omega naught over t. What's omega f? 20. What's omega naught? 0. What's t? 5. So what's alpha? 4 radians per second squared. And there we go. I know how to do this type of problem in linear kinematics, so let me think about it as if it's a linear kinematics problem first, figure out how I would solve it, and then replace the equation. What about part B? Well, part B says, I want to know theta. Okay, so I want to know a distance. How far did this object go? Well, I could either use the first equation or the second equation. It doesn't matter which I choose, so let's just choose one. Let's say I want to choose the first one. Okay, so I would say x equals v naught t plus 1/2 at squared. And say I know a is 4, t is 5, v naught, that's 0. I'm looking for x. But remember, this isn't linear, this is rotational. So I should actually do theta is omega naught t plus 1/2 alpha t squared. Theta is omega naught, which is 0, times t, plus 1/2 alpha, which I just calculated was 4, t squared. That's 0. So 1/2 of 4 is 2. 5 squared is 25. 2 times 25 is 50 radians. And there we go. So, it's up to you which way you like doing this. Either just go ahead and start with the angular equations and try to plug the numbers in. If you can do that, fine. That's perfect. If you're not used to it yet, if you're uncomfortable with the rotational stuff, then start with the linear stuff. Reread the question as if it's a linear question. So for this one, the question says a wheel starts from rest and begins to rotate, eventually getting to this 20 radians per second in 5 seconds. What's the angular acceleration? Well, instead of listening to it like that, think about it like a car starts from rest and begins to drive, reaching a final velocity of 20 meters per second in 5 seconds. What's the acceleration of the car? Well, you did that back when we did kinematics. So set up the equation as if that's what you're going to solve, which is what this is here. But then convert the variables. Once it's converted to this, now you know what to plug in. That's the other way to do it. And I found that for the beginning, usually people like to do that. And then after a while, they're used to it. They don't have to think about the linear stuff anymore. Now, one more thing I want to talk about is the units here. Theta is in radians. Omega is radians per second, and so forth. A lot of times you might see a problem which deals with revolutions. So, for instance, a wheel spins 3 revolutions. Or RPM is another unit. RPM means revolutions per minute instead of radians per second. Okay, bad units. If you see these units like revolutions or RPM, you have to convert. So I'll go ahead and show you how to convert. 1 revolution means a full time around is 2 pi radians. So if I say theta is 3 revolutions, you have to be able to convert that and say, well, if 1 revolution is 2 pi radians, 3 revolutions better be 2 pi times 3, which is 6 pi radians. Okay. What about if I have RPM? Let's say I tell you omega is 10 RPM. Or 10 revolutions per minute. How would you convert? Well, you convert just like you convert anything. First of all, I don't like revolutions, so let me convert away from revolutions. And what I know is 1 revolution is 2 pi radians. And now I could cancel revolutions, and now I'm at radians. So that's good. Minutes is bad, though. I don't like minutes, I want seconds. So I need to multiply by something to get rid of the minutes. Since the minutes is on the bottom over here, it has to go on top here. And what I know is that 1 minute is 60 seconds. So now I cancel minutes, and I'm left with radians per second. Now all I have to do is multiply through. 10 times 2 pi, that's 20 pi. And the bottom is 1 times 60. So 2 over 6, this is pi over 3 radians per second. Okay? So you just need to know. So just be careful given a problem, you're in the right units. If everything is radians per second, things like that, no conversions necessary. But if you do see a problem with revolutions or RPM or something like that, something that's not radians per second, you need to convert to make sure you're in the right units. It's just like before. If instead of having meters, you were given feet or you were given centimeters, then you have to convert to meters first. Well, here, just convert to radians first. But this is rotational kinematics. You're going to find, I'll post, of course, on Canvas, a set of practice problems. And when you read through the problems, as long as you get away in your mind from what, the rotating, rotational stuff, blah, blah, blah. If you just think about the problem, you're going to find that the problems sound very similar to the kinematics problems. The good news is, what made kinematics hard or more complicated was having to worry about X and Y components. If things were at an angle, or a cannonball is shot at an angle, or a cannonball is shot, or you throw a ball horizontally off a cliff, the ball can move both up and down and left and right, and you have to keep X separate from Y and all that stuff. Here, with rotational, there's none of that. So it's purely just the equations. Thus, you focus less on the components, X and Y separate, and you can focus more on what's the question asking, which equation should I use, plug my numbers in. The only place you can get tripped up is with converting. If you're using wrong units, you're going to get a wrong answer. All right, so that's all I have for this theory here. Again, be on the lookout for the practice problems. Start working through them as soon as you can. I'll let you know if there's any homework problems necessary. And we will continue on from here. Until next time.